In our previous class, we looked at examples for material balance in single unit. We did solve for example number 1, example number 2, and example number 4. For example number 3 and example number 5, I've asked you to go back home and try it on your own. And we're going to discuss it for today. So, who would like to give me the answer? So, if you look at example number 3, I think we have 3 unknowns, which is the, if I just draw it very fast. So you have 3 streams coming in. One is the spent acid, the other one is the concentrated sulfuric acid, and the other one is the concentrated nitric acid to make a final composition of our acid composition. So I think we have discussed, I've given you the flow chart, and the unknown is the spent acid flow rate, the concentrated sulfuric acid flow rate, and also the concentrated nitric acid flow rate. So we have these 3 flow rate. We have done the degree of freedom analysis. We got that degree of freedom, right? We have the number of unknown is equal to 3. Number of independent equation is equal to 3. So we have number of degree of freedom is equal to 0, meaning that this question can be solved. So who would like to give me the first answer? What is the flow rate for the spent acid? Anybody? What is? So I put, for me, F1 is the flow rate of spent acid. So F1, what is the answer? Flow rate for F1 is equal to 136.17. Okay, so this is the first answer. 136.26. Okay, 26. Okay, that is the flow rate for first one. What is the flow rate for concentrated sulfuric acid, which I think it's, for me, it's F2. Okay, concentrated acid. So concentrated sulfuric acid, for me, it's F2. F2 is equal to, what is the flow rate of F2? Six 635.9, 635.9. Okay, 635.9. Okay, and the final one is the flow rate for your concentrated nitric acid. What is the answer for the final one? 227.91. Okay, 227.91. Did everybody got this kind of answer? Okay, so 227.8. Okay, so as long as you get answer similar to this one, then your answer is correct. But the only thing that I would like to stress to you is that you have to make sure that, in order for you to make sure whether your answer are right or wrong, right, there's always the step number 7 where you check your answer. Okay, you have to check your answer. So how do you check? The best way is that this is your product stream, and we know that our product P here must always equal to 1000 pound per hour. So the best way for you to check whether your answer is right or wrong, just try to find F1 plus F2 plus F3 must always equal to 1000. So if you can get F1 plus F2 plus F3 is equal to 1000, then you know that your answer are correct. So sometimes when you do this, so it is important for you to make sure that you are focusing on your decimal number and your significant figures. Okay, sometimes if you put very high decimal numbers, a lot of decimal numbers, you'll get a value of sometimes 999.99 something, 7, something like that. So this is also acceptable. And sometimes if I have these three number, if I add up everything, I'll get around 1000.291. Okay, so you can see here, because of our decimal number, we are getting this 291 value. So as long as you can get value something like this and something like this, the 999 or 1000.2, the value is acceptable. The only way you get your answer is wrong if, let's say, the answer is 1000, all of a sudden you get 962 point something. This is wrong. So if this is how you get your answer, final answer, please go back and check your decimal point and your significant figures. Sometimes there will be a lot of difference between 136.6 and 136.55. It can make a lot of difference, even though it's just 0.05, but can make a lot of difference when you are adding and when you are times and dividing all these things. So make sure after you have gotten all these three values, you try to get this F1 plus F2 plus F3 must always equal to 1000. Okay, so everybody can get this final answer. So these three answers are correct answer. Anybody have any problem solving this problem? Anyone have any issues? Can I give the answer in fraction? As long as your answer at the end of the day, you'll get back 1000. So there's no problem if you give in fraction. As long as the fractions are correct, and when you add in all the fractions, you'll get back 1000. Because you must always remember, this is a open system, continuous process, and also a steady state system, meaning that whatever is going in must come out. Input must always equal to output. So if you give in fraction, if you give in decimal points, as long as you can get back the original 1000, that should be okay. So far we have done material balance for single unit, where you have only one mixer, one separator, one operator, and so on and so forth. But today we're going to be looking at what if we have more than one unit. So if you see here, this is example where you have at least 2 units here. Okay, so example number 6 is saying that a label flowchart shows a continuous steady state 2-unit operation as shown below. Each stream contains 2 components, A and B, in different proportions. 3 streams whose flow rates and or composition are not known are labeled as 1, 2, and 3. So if you see here, we have this unit 1. Okay, so let's say this is, I put unit number 1, this is unit number 2, or let me just put because we have make it confused, so I'll just put here unit X, and this one is unit Y. Okay, so we want to find the flow rate, which is flow rate number 1, flow rate number 2, and flow rate number 3, right? So we have to find not only the flow rate, but also the composition of each flow rate. So if you see here, first of all, we have to define our system. So if you remember our previous classes, we can say that system is whatever you define to be a system. It can be as long as you put a boundary, then that thing is called your system. So for me here, I can say that this is my first system. This X unit is my first system. This is my another second system, my Y unit here, where separation is happening. And then I can also say that this is also a system, because I see that there is mixing happening here. So I have 3 systems, and also I can put here an overall system. So in total, I can have 4 systems. Okay, so if you have 4 systems, so you have to make sure that this is where degree of freedom analysis is very important. So you have to make sure that all your systems, all your informations are there, and then only you try to solve for each, for the overall and for the each system. So here we have to find the mass composition of number 1, number 2, and also number 3. So we have to find the flow rate and mass composition. So how do you do this? So the first way is that we try to identify the system, and then we do degree of freedom analysis on each system. Because if you just start solving it, sometimes there might not be enough information for you to solve it, and then you'll be wasting your time. So after you have identified your system, so for me, I said there are 4 systems. So I will do degree of freedom analysis on each of the systems. So this is my unit X, and this is going here. So I just do degree of freedom analysis on this system. So here I know that just now it was number 1. So I can say that this is my P1 stream, and I have here weight fraction of A1 and weight fraction of B1. So the reason I'm putting A1, B1 here, so it is easier for me to identify which stream or which unknowns am I referring to, because we can have a lot of unknowns after this. So now, if I look at here, everything is labeled. I have my basis of 140. So I've done step 1 until step 3. Now I want to find my degree of freedom. So first of all, I find my degree number of unknown. So I see here I have unknown flow rate, which is my P1, and I have unknown mass fraction of A and mass fraction of B. So I say that my degree of freedom is 3. Now I find again we find the number of independent equation. So I see here I have 2 components here, A and B. So automatically I say that I have 2 independent equations, which is A and B. And then I can relate my mass fraction, and I can have an implicit relation. So I can say I have another independent equation. So my degree of freedom is equal to 0. So this problem, this part of the system can be solved. No problem. Okay. So then we move on to our mixing point. So here, this is the P1 here is still P1. So I can label again here, this is P1, this is WA1 and WP1, and then it's mixing with 30 kilo of A and B. And then if you remember our overall system, this is our stream number 2, where we don't know the mass composition and mass flow rate. So I put here my P2. So the same thing here, if I have my P2, then I have a mass fraction of A2 and mass fraction of B2. So 2 here is representing the stream 2. So now I have labeled, everything is there. I have my basis. So I do number of unknown. I have 1, 2, 3, 4, 5, 6. Right? This is the number of unknown I have. Number of equation that I can make is that I have 2 species, so 2 independent equation, and I can make an implicit relation for mass fraction in stream 1 and mass fraction in stream 2. So I can say I can add +1 and +1. So you see here, now my degree of freedom is equal to 2. So this point I cannot solve yet. Unless, so the only way I can solve is that I have two additional information. So let's say if I do another method, another degree of freedom, I say that my unknowns is equal to 3 only. So how did I get this 3? I'm assuming that first of all, I have solved for unit X. If I solve for unit X, I can already get this value. So if I get this value, these 3 value here, the P1, W1 on the mixing is no longer my variables. They are the known values. So the only variable I have is my P2, WA2 and B2. So based on that, I can say that my degree of freedom is only 3. It's no longer 6 because these 3 value I already know. I already know the value of these 3 things here. Right? So now, if I do that, then I say that my number of equation is equal to 2 for each species and 1 for the mass fraction relation. So here I have degree of freedom equal to 0. That is why it is important for you to define your system properly. Now we have our second unit, which we label as Y, right? So here again, this is P2 coming in into the Y unit, and we have WA2 and we have WB2. And then leaving here is our stream number 3, right? So we can say that this is my P3, where I have WA3 and WB3. So if we do degree of freedom analysis just on this unit, so I know that my number of unknown is equal to 6 again, because 1, 2, 3 is over here and 4, 5, 6 is on this part. My number of independent equation, again, it's 2 plus 1 plus 1. So again, I have a degree of freedom is equal to 2. The same thing, if I solve this part of the system after I have solved this part of the system, I will know these 3 value. So if I know these 3 value, I will have number of unknowns is equal to 3, number of independent equation is equal to 2 plus 1, and then I'll have degree of freedom is equal to 0. So that is why it is important for you to do degree of freedom analysis properly, so you know where you need to start. Because if you start here, definitely you cannot solve. So you have to start with unit X first. So this is my third system. I also have my overall system, which I said that this is my boundary for my overall system. Okay, so if I were to redraw again, just ignoring this X and Y inside here. So this is again Y, this is my X. So if we ignore that, we just draw the overall. So I know that I have one stream coming in, which is this 100, right? I have this 100 coming in, kg per hour. And then I have one leaving, which is my 40 kg per hour. And then I have another one leaving, which is my 30 kg per hour. I have my stream 3, which is this one, leaving. So this is my P3. And then I have one coming in here, which is this 30. So one is still coming in. So this is 30 kg per hour. So now, if you see here, I have, I'm not going to write component A, component B for everybody. So for P3 here, again, I have my WA3 and WB3. So if I do degree of freedom on this side, on this overall system, I know that my number of unknown is equal to 3. My number of independent equation, since I have A and B for all the streams, so 2 for component plus 1 implicit relation between the mass fraction. So 2 plus 1 is equal to 3. So I have my degree of freedom is equal to 0 again. So I can say that I can solve based on my degree of freedom analysis. If I put here solvable, I can solve for unit 1 and unit X, okay, or unit X and our overall. That is the only thing I can solve. For my, so cannot solve is my mixing and my unit Y. Meaning here that unless I solve either unit X and overall, then only I can solve my unit Y or mixing. So having known this, then I can start strategizing on which one I would like to solve first. So now the most easiest way, if I look at this system, I say that by looking at system A, system X, system Y, system mixing, and system overall system, for me, I find that the overall system is the easiest way for me to start solving. Why? Because I have all the inputs and only these 3 variables. So this is going to be easy for me. So once you have done degree of freedom, then you have to write your equations. So let's say first of all, I do balance on the overall system. So overall system. Okay, I'll start with the overall system. I do balance overall. So balance overall meaning that this is an open system, continuous process, and steady state system. So input must always equal to output. So I know that on my input side, I have 100 plus 30 here. This one and this one is my input. So 100 plus 30, and everything else is my output. So it's equal to 40 plus 30 plus P3. So from here straight away I can get the value of P3 is equal to 60 kg per hour. Okay, so I've solved for one of my variables here. So the next one I can do, and I can find the value of WA and also WA3 and WB3. So once I can do balance of A or balance on B. So let's say if I do balance on A. Okay, so if let's say I do balance on A. So balance on A meaning here that whatever here I have A, so I have A here is 0.5 times 100 on this stream. On this stream I have 0.5 A plus I have A here on this stream, so I have plus 0.3 A times 30 is equal to, for the 40 kilo I have 0.9. Okay, so 0.9 times 40 plus 0.43 is 0.6. 0.6 times 30 for this stream plus WA3 times 60, which I just got from here. So if I solve this, I'll get the value of WA3 is equal to around 0.0833. Okay, this is my weight fraction, and then I know that WA3 plus WA2 is WA3 plus WB3 is equal to 1. So I can get my WB3 is equal to 0.9987. Okay, so this is, I've solved for my stream number 3. So now the only thing we have is we are going to solve for stream number 1 and stream number 2, which is our P1 and our P2. So we can start doing balance again on, let's say we do on unit X. So I'll just draw again unit X. We have input, we have output, and we have P1. Right? So now we do balance overall again. Right? We do balance overall. So we know that for unit X, 100 is coming in here. This is 100. 100 is equal to 40 is leaving plus P1. So automatically I can get P1 is equal to 60 kg per hour. So the same thing I can do balance on A. Okay, if I do balance on A, so I will get a value of WA1 is equal to 0.2333 and my WB1 is equal to 0.7667. Once I have gotten this value, I know that my P1 is connected to my mixing point. So again, if let's say we write again for our mixing point. So let's say this is your mixing point, right? So this one is your P1, WA1 and WB1. You are adding with 30 kg per hour. So you will get your P2, WA2 and WB2. So again, once I have known this value, which I just calculated, 60, P1 is equal to 60, WA1 is equal to 0.2333, and then WB1 is equal to 0.7667. So now if you see here, we know we can solve this question because we already did our degree of freedom. So my final answer is that I can get P2 is equal to 90 kg per hour, and then my WA1, WA2 is equal to 0.2555, and then my WB2 is equal to 0.745, 0.7445, sorry. 7445. So I've gotten the value for stream 1, stream 2, and also stream 3. So that is how you solve for your multiple unit material balance.